Now, why depth sorting is required? Now, see, the idea is that uh, every tile will have many 3D Gaussians which will overlap, which will contribute. So now every 3D Gaussian will have a depth and we have to sort it because see Gaussians, they are transparent volumes, not opaque surfaces. So every Gaussian, 3D Gaussian will contribute. So therefore rendering order affects the result. So correct approach is blend from front to back. So this is like very important. So we have multiple Gaussians. So we have to blend from front to back in this way, front to back. So this is like the first Gaussian, second Gaussian, third Gaussian, 3D Gaussian. So you have to blend from front to back. So high priority should be given because the front will be the one which will be of topmost priority, then second Gaussian, then third Gaussian. So blending will be from front to back. This is how it will be done. Now the sorting method we will be using is Radix Sort. Okay. Now see, the idea is that every 3D Gaussian, it will be having a depth associated with it because when we will be when we splat based on the size, shape and orientation, a depth will be calculated for every 3D Gaussian on a tile. And we will be sorting the depth. And the sorting method we will be using is the Radix sort. So each tile will sort its Gaussians using the Radix sort. Now see, Radix sort, how the sorting is done using the Radix sort. So in Radix sort, what we do is that whatever the numbers we have, first we will sort the unit place, then the tens place, then hundreds place. I'll give you an example. Like for simplicity, I'll just take 2 digit. Now let us suppose I have to sort it in ascending order. So what I'll do is first I'll sort the unit place. So based on the unit place sorting, 50 should come first, then 12, then 24, then 35, then 16, then the tens place. And it's a stable sort. So order I will preserve like 12 and 16 both have one in the tens place. So since I'll preserve the order, 12 will come first, then 16, then 24, then 35, then 50. So now see, I sorted the number and it is like very efficient. It's very fast, efficient. And if I convert it into binary, it will be even more efficient. So that's like an example of a Radix sort. And that is what, so here these numbers will be the depth of the Gaussians and using the Radix sort will sort it. So it is fast on GPU, works well for large arrays, predictable performance, and it is parallelizable. And that's very important. It is parallelizable. It will make it even more fast. And the sorting key we will be using is the depth value. So the idea is, say tiles, they will be having like every tile will be having like lots of 3D Gaussians. We will use the Radix sort to sort based on the depth values. I'll get the sorted key per tile, and that will tell us that okay, which 3D Gaussian will be on the top, then like that, the priority. So this is how it will be done. So that is the Radix sort. So that is depth sorting. Then alpha blending. So for alpha blending, we will do front to back compositing. So one after depth sorting, we will get the 3D Gaussian on a tile in a order. And from front to back, compositing will do. And how we'll do the compositing, let's understand. So for each pixel, we accumulate color contributions because we know that all the 3D Gaussians will contribute to a particular pixel. Like in a tile, a pixel of that tile, its color value will be determined by the all the 3D Gaussians which are contributing in that region. So that is what is alpha blending is. If we talk about the alpha blending equation, so alpha blending equation, so the idea is, this is the alpha blending equation. Let's understand its working. So C is the accumulated color. So here, see, initially C can be like nothing. It can be zero initially, accumulated color. Now see, alpha I is the opacity of a 3D Gaussian. Of the ith, alpha is the opacity of the ith Gaussian, and Ci is the Gaussian color of the ith 3D Gaussian, and T is the transparency, and this transparency will keep on updating it. Okay, now I'll tell you, and this is the formula for transparency. Now we'll get a feel of it, like how this is working. Okay, so in order to understand this, so let me just get rid of all the lines and all. Just I'll highlight the formula. So we just have to focus on this alpha blending equation. Now let us see how it works. Okay, so for the first 3D Gaussian, like G1 is the first 3D Gaussian. For this, the remaining transparency is zero. Because see, the idea is that for the front Gaussian, it has to be fully transparent. Because we are starting from there, it is fully visible. The first Gaussian, the first 3D Gaussian is fully visible. So T will be zero. T will be zero means it is fully transparent. So the E and C will be zero. So the accumulated color will be the opacity of that Gaussian and the Gaussian color of that Gaussian. We'll just multiply that. So we will get the value of C. So for this, it will be alpha 1 C1. We'll write it properly. So alpha 1 C1, that is the uh, color, accumulated color. Now, if we go to the second Gaussian, like the second 3D Gaussian, now what is happening for this? See, it will be hidden to a certain extent by G1 because it will be on the back of G1. So the T will be different for it. So the value of T will depend on the value of previous alpha. So the value of T, the transparency of this G2 will depend on alpha 1. So it will be 1 minus alpha 1. So we call it the remaining transparency. So the remaining transparency will be 1 minus alpha 1 because alpha 1 has, it is opaque in certain, like if it is 70% solid, so G2 will be 30% transparent. If it is 80% solid, then G2 will be only 20% transparency. So the remaining transparency will depend on the alpha 1 for G2. So the T will be like that. So the idea is that now the accumulated color, what will be the contribution of G2? The contribution of G2 will be 1 minus alpha 1. Contribution of G2 will be 1 minus alpha 1 times alpha 2 C2. And like that, the contribution of G3 will be 1 minus alpha 1 into alpha 2. That is the previous transparency. That's the remaining transparency multiplied by alpha 3 G3, C3. Like that it will be. And we will just add all this, and that is the accumulated color we will get. So this is the alpha blending equation, and it makes sense also. So this alpha blending equation, it will give us the final pixel color, and that is making perfect sense. If we talk about meaning of T and early termination, okay, so meaning of T we already saw, remaining transparency. So T represents how much background light is still visible. When T is approaching towards zero, it means we are becoming more and more transparent. Rendering can stop early. Acha, T remaining transparency. So if remaining transparency is approaching to zero, it means the transparency is now, remaining transparency is close to zero, means now the subsequent 3D Gaussian, they are not visible at all. So when T will start approaching towards zero, when t will start approaching towards 0, we can stop early. And that is an optimization. And that is what is early termination is. For example, let us suppose first two Gaussian itself, they like occupied more than 99% of the region. So remaining transparency is like very less. We can stop early. That is the early termination. So early termination optimization. So stop processing remaining Gaussians if remaining transparency it approaches 0. This saves large amount of computation. This is very, because see, the idea is that for a particular, to render a particular pixel, we can have hundreds of Gaussians, but only first three Gaussians are contributing. First three Gaussians are occupying all the visible space. And from the fourth Gaussian, the remaining transparency is 0. It means it is not at all visible. And if it is not visible, it cannot contribute. So we can eliminate all the subsequent Gaussians. So that is the early termination optimization. And in this way, we are even more optimizing it. So now the idea is very clear. Okay, in 3D Gaussian splatting, because of that uh, frustum queuing, millions of Gaussian, we are eliminating it, and we are just considering thousands of Gaussian. Then we are dividing the scene into tiles. So every tile will be dealing with hundreds of Gaussian. And in that also, we are doing the depth sort. And when we are doing the alpha blending, we will be considering only the first few Gaussians, and we will be eliminating the rest of the Gaussians. In this way, we are optimizing the process, and hence we are able to achieve the real-time processing, real-time rendering